everybody. Let's get a little practice for the next test we're going to take on geometry about areas. And I got an array of questions right here. We'll walk through them. It's a lot like the test you'll have to take. Got this rectangle, and its length is 3a plus b, and its width is 2a minus 3b. We can measure those out, but we're just going to get the product of those, the length and the width, and that'll be the area for what we figure. So the length is 3a plus b, 1b I'm thinking, times 2a minus 3b. And we're going to multiply the first term times the first term for sure, and that'll be 6a squared. The outside terms will give me a negative 9ab. The inside terms will give me a positive 2ab. Yeah, those are going to go together, aren't they? Plus, and the last one times the last one, a positive b times a negative 3b, that gives me a negative 3b squared. So I'm going to clean that up. Call that 6a squared. That negative 9 positive 2 gives me a negative 7ab minus 3b squared. And I just multiplied those two binomials. And that's the area of that rectangle. Here we get a chance to use Heron's formula. I'm going to need a calculator for that. But let me remind you of Heron's formula. It looks like the area of the triangle will be given by the square root of the semi-perimeter minus the semi-perimeter times the semi-perimeter minus each of the three sides. S minus A times S minus B times S minus C. Where these sides are A, B, and C. And it tells me that side little a is 17, side little b is 10, and side C is 21. S stands for the semi-perimeter. I would make a note what the perimeter truly is, and adding these up I see 31 and 17, that's going to be 48. So the perimeter is 48. Therefore the semi-perimeter is 1/2 of the perimeter, that's 24. So we would have the square root of the semi-perimeter, 24, times, and the semi-perimeter minus each of these sides. So 24 minus 17 is going to yield 7. 24 minus 10 will be 14. And 24 minus 21 will be 3. And it's fun to work with those, but I'm going to hit it with a calculator and see what happens there. So I have that, the square root of 24 times 7 times 14 times 3. And I enter, and it tells me it's 84. So there, that triangle's 84. That's just a calculator-driven thing, but knowing the formula is important. Now, this is a good question. Find the length of altitude AB. Oh, altitude to base AB. And here's base AB. This would be that altitude we care about right there. Not a special triangle that I know about, not a 30, 60, 90 triangle, but what I do know is we have the formula for the area of a triangle. It's equal to 1/2 times the base times the height. And if you give me the base and the height, I'd give you the area. But if I already knew the area for some reason, and I already knew the base that I wanted to use, I could use this relationship to figure out the height. That's what we ought to do. The area of our triangle by Hero's formula was 84. That ought to equal 1/2 times, and the base we're using, since we would like to know the altitude to base AB, must be 21. Times, let's call that X, or maybe H for height. And I don't like 1/2 of 21 so much, so I multiply both sides by 2, get 168 is equal to 21 times H. Divide both sides by 21 and declare the height to be, well, let's start with 168 over 21. And I guess that's going to be 8, isn't it? Alexa, what's 8 times 21?
8 times 21 is 168.
Yeah. So this must have been 8. I'm looking back at this thing. If that was 8 and this is 10, this must have been 6. That's a 6, 8, 10. And this is 8, 15, 17. Yeah. That's why that was 21. So I do think that it was in fact true that that was 8. It does fit with the Pythagorean triples I'm aware of. Hey, let's play a little bit more. All you had to do was figure out the altitude would have been 8. But it does make sense that it would have been. Here we have an isosceles triangle. And there's a kind of a clever way you can find its area. I would call this as the base, the 14, and show the altitude to the base. And in an isosceles triangle, the altitude is going to be going to bisect that angle, and it's going to give us two congruent triangles. So these lengths would have been 7 and 7. And I'm going to call that altitude A and hit it with the Pythagorean theorem. I'm going to find the area of this triangle in a moment. So once I get that area, once I get that altitude, and it's true that a squared plus 7 squared is the Pythagorean theorem equals 25 squared. And this is going to be 24. A squared plus 49 is equal to 625. Subtract 49 from both sides, you got a squared is equal to 576, and then take the square root of both sides, and a is 24, as a matter of fact. It's a Pythagorean triple, some of us might have known. Now that I got that in place, going to get the area of the triangle. Getting a little bit crowded. 1/2 times the base. Base is 14 times the height, 24. I can handle that. The area of the triangle is a half of 14 would be 7, and 7 times 24 is 168, I think. 7 times 24, 168, yeah. That's the area of that triangle, I think. Now we got an obtuse triangle. Let's see what happens here. And we'd like to find its area. I want to get the area of these things. I don't have a good altitude, do you see? But I think I could get one if I extend this side and go from vertex C to that side, to that line perpendicularly. That'll be the altitude of our triangle right there. I'm going to work with this angle. I see that it's 135 degrees. Yielding this guy, going to have to be 45, as these two are supplementary. If that's 45 and that's 90, this is a 45, 45, 90, with a hypotenuse of length 16, I think it is. That's an obtuse triangle. This is 16 and this is 10. In a 45, 45, 90, to go from the hypotenuse to the congruent side, you divide by the square root of 2, and 16 divided by the square root of 2 is going to give me 8 square roots of 2 for the altitude. This length would also be 8 square roots of 2, but we don't care. I got the altitude, that's what I care about. Let's go with the area of the triangle is 1/2 times the base times the height. That would be 1/2 times, and the base of our triangle is this length 10, just that much, and the height therefore 8 square roots of 2. Half of 10 is going to give me 5 times that 8 is going to give us 40 root 2 units squared for the area of that triangle. Hey, we got a parallelogram. Let's play. You're knowing that the area of a parallelogram is going to be the base times the height equals the area of that parallelogram. We got this length is 12, and opposite sides of a parallelogram are congruent, so this would have also been 12. And we'll let that be our base. But if that's the base, we'll need a height that is perpendicular. And there we have it, yielding the beloved 30, 60, 90 triangle, the hypotenuse of which is 8. Therefore, the short side would have been 4. And the longer leg, 4 square roots of 3. And then we're all downhill. Let's just get the area of that fella. Area will be the base, that's 12, times the height, 4 root 3. We have to call that 48 square roots of 3. Now here we got a rhombus. There's a couple of ways you can do that. But what you got to remember about a rhombus is that it's equilateral. All those sides are going to be 13 if this one is. And SQ is 10, and the sides are, the diagonals are perpendicular and bisect one another. So if SQ is 10, this part would have been 5, and that part would have been 5. And I think we're going to work with the Pythagorean theorem as we try to seek the length of this other diagonal, this distance first, with the right triangle that I'm shading right there. Hypotenuse is 15, and there's a side of length 5. I hope that you know this length already, this other leg, because 5 squared plus 12 squared, that's a Pythagorean's triple, is equal to 13 squared. So I'm sure that this length would have been 12. This length would have also been 12. Therefore, that diagonal, PR, must be 24. And the clever way to get the area of a rhombus is diagonal 1 times diagonal 2, the product of the diagonals divided by 2. 1/2 the product of the diagonals. So in our case, that would be 10 times 24 divided by 2. And that's got to be 12 times 10, the same thing, 120. But I like to check things, and probably you should too. I'd say, what's the area of that triangle right there? And you could go 1/2 times its base, and you could let the 12 be the base. And if 12 were the base, the appropriate height would have been the 5, as it's perpendicular. And a half of 12 is going to give us 6 times 5 gives us 30 units for that triangle. And since there are 4 triangles just that size, that does indicate to be 120. So I'm happy with what we've done. Hey, let's play with the trapezoid. And in class, you would work these before I do. I'm going to give you a chance to think them through. And the kids at home ought to do the same thing, working before I do this. But every time you get near a trapezoid, you're going to show those altitudes at either endpoint of the upper base. I can't imagine when you wouldn't. At least not when you're studying the area. So we're going to set up those couple of altitudes, giving us right triangles with a 30, 60, 90 right there, it looks like. Let's go ahead and bust through for those numbers. Short side would have been half the hypotenuse, and the longer leg, the altitude is 8 root 3. Huh? Interestingly, this is isosceles. There's another 8 root 3 over there if we cared about it, and this length would have been also 8. This rectangle in the middle, opposite sides are congruent, so this length would have been 12. A couple ways we could work it, but I'm going to go with the formula for a trapezoid. Base 1 plus base 2 divided by 2 times the altitude. Base 1, I could call that one 12, and the other base is 28. Add them up, divide by 2, they're going to multiply by the altitude, which is 8 root 3. Really the trick here is knowing how to use a 30, 60, 90 triangle, huh? And this is going to give me 40 divided by 2, therefore 20 times 8 root 3. We'd have to call that 160 square roots of 3. Yeah, we got to do the pieces, huh? What would be that triangle right there? 1/2 times the base times the height, that'd be 4 times 8 root 3, be 32 root 3 for that triangle. There's a rectangle in the middle. 8 times 12 is 96, that'd be 96 root 3. Got to add up the parts, you see. And this wouldn't be as big as that one, so 1/2, 4 times 8 is going to give us 32 root 3. Those give me 64 plus 96, that'd be 160. So I'm happy. I think we got it right. And this is more fun. Look at this, a non-isosceles trapezoid. Nonetheless, we're going to drop those altitudes at either endpoint of the upper base. 30, 60, 90. Now let's make that short side be half the hypotenuse, and the longer leg, short side times the square root of 3. Opposite sides of a rectangle are congruent. So this would have also been 6. And hey, you know about this leg right there? Yeah, it ought to be 8, huh? I'm absolutely certain that 6 squared plus 8 squared is equal to 10 squared. That's a triple that I've come to know. Now I think we got this trapezoid all figured out. We'll go with base 1, that's 10, plus base 2, 18, plus 6 root 3. Careful there. Add those spaces up, divide by 2. And then we'll multiply by the altitude, just that 6. Now here, we have 28, which we can divide by 2, and that'll give me 14. Plus, the 6 square roots of 3 divided by 2 gives me 3 square roots of 3. Just want to clean up this before I multiply it by 6. And now I could, and 6 times 14 is probably 84, plus 18 root 3. I don't know what you're thinking when you said, let's do those parts and see if it adds up that way. And I think we got this, I think that would be the 18 root 3 right there, huh? 1/2 times the base would be 3 root 3 times 6 would be 18 root 3. That's this part, and let's see what these add up to. This part would be 60, wouldn't it? 10 times 6 is going to be 60 there. And this triangle, 1/2 times the base times the height, that'd be 4 times, that'd be 24, wouldn't it? So that gives me the 84 and the 18 root 3. So I'm happy with that. I'm sure we got it right. Let's play some more. This other page looks a little more interesting. Here we got a sector of a circle. They're giving us the radius. The radius is 10. I'd be thinking about the circumference in the area right away, man. Circumference is given by 2 pi r. We'll need it. Area of a circle is going to be given by pi times the radius squared. Okay, so with our radius of 10, and the measure of angle BXA is 120. Now, I'm not sure what's going to happen on your quiz. It could be 135, 120, 90, 60. It's going to be something that has common factors with 360, so you're going to reduce that fraction. It asks for the length of arc AB, and right off the bat, I would be thinking, well, it's going to be 120 3/60ths of the full circumference. And the circumference of this circle, 2 times pi times the radius, would be 20 pi. I have 1/3 of 20 pi. And I can't call that anything but 20 pi thirds. That's what we ought to do. You can call that 6 2/3 pi, yeah, I know, but 20 pi thirds is what we should. That's the length of arc AB. Oh, and the length of arc ACB. Now that's going the other way. And what I know it must be twice as big as this. If this is 120, wouldn't this be 240? But there's other ways we can think about that. What's the full circumference? And the full circumference was 20 pi. And from that, we ought to subtract what we had here that was on arc AB, and we'll have the other arc, the complement, minus 20 pi thirds. Yeah, you need a common denominator to do that, wouldn't you? And this 20 pi is really the same as 60 pi thirds minus 20 pi thirds. As I subtract these fractions, the 20 pi is really the same as 60 pi thirds, and then we would get 40 pi thirds, wouldn't we? And it does make sense that that's twice as much as this, because this is 240 degrees of arc, and that's 120. Let's play some more. Get the area of the sector. Well, it's going to be 120 3/60ths of the area of the whole circle. Area of the full circle would be pi times the radius squared, and the radius is 10, so therefore 100 pi. So we're talking about 1/3 of 100 pi. I have to call it 100 pi thirds for the area of the sector. You could call it 33 1/3 pi, but I'm telling you 100 pi thirds is nicer. Show an altitude of the triangle and find its length. And I'm going to extend this base and get to it perpendicularly, best I could. Because that's a 120 degree angle, I'll have a 60 right there. These 30, 60, 90 triangles will not go away. I do know the hypotenuse, as it's the radius of the circle, and the radius was 10. In that 30, 60, 90 triangle, the short side would have been half the hypotenuse, would have been 5, and the longer leg would have been 5 times the square root of 3. So the altitude, and find this length, there it is. The altitude is 5 times the square root of 3. Give the area of that triangle AXB. Let's go with 1/2 times its base, 10, times its height, 5 root 3. What do you get when you do that? I'm getting the 5 times 5 root 3, calling it 25 square roots of 3. Happy with that. Moving to the last part of this question, give the area of the segment defined by chord AB. And this chord shown that we're going to have to agree that this is the segment, the thing that I'm cross-hashing right now. And what it has to be is the sector, bounded by the radius and the arc, minus the triangle. That altitude's kind of in the way, but here we're going to go. I'm going to make a statement about that. The area of the sector minus the area of the triangle equals the area that is shaded. We have the area of the sector. It was 100 pi thirds. Minus, we have the area of the triangle, 25 square roots of 3. And I hope, now we're getting to some funny looking answers, aren't we? To me, that's a beautiful answer, and it's something you might want to get used to, but yeah, 100 pi thirds minus 25 square roots of 3 for the area of that segment, right there. I do like this picture. Here's a place to pay attention. This is what we would call a composite figure. It has a regular hexagon with a right triangle and an equilateral triangle. And a semicircle all stuck together. We're going to find the area that's bare, the total area momentarily. We'll read through it with you. Triangle ABC is a right triangle with legs of length, and they're telling me 12 and 16. We'd want to know that hypotenuse right away, wouldn't we? And I hope you recognize that's a big 3, 4, 5 triangle there. 12 squared plus 16 squared. Yeah, that's going to be 20 squared. 144 plus 256 is going to be 400, but really, if you're thinking of this as a 3, 4, 5, 3 times 4, and 4 times 4, and 5 times 4, that hypotenuse is going to be 20. So this is going to be 10 and 10, isn't it, as we're thinking about the radius of that semicircle. Give the area of triangle ABC. That's the right triangle in the center. Huh? And that'll be easy enough. 1/2 times its base, 12. 12 times its height, 16. And a half of that 12 is going to yield me with 6 times 16. There's 96 units squared for the area of the triangle in the middle. The area of the semicircle. I'll be thinking to myself, well, the area of a circle is going to be pi r squared. So the area of this full circle would have been 100 pi, but we don't have a full circle, we got a semicircle. That's going to be half as much, that'd be 50 pi. How about the area of that equilateral triangle? Well, there's a couple ways you could do that. But I'm realizing that it's 16 on a side, isn't it? I like side squared, squared to 3 over 4 myself, but I'm going to work it this way. If this side were 16 and that side were 16, this would have been 8. The short side's half the hypotenuse, and this would have been 8 root 3. And if you would have gone 1/2 times the base times the height, a half of that base would be 8 times that height. 8 root 3 is going to give you 64 root 3. I'm thinking that's the area of the triangle. 64 square roots of 3. I could have gone with side squared square roots of 3 over 4. That's a nice formula for the area of an equilateral triangle. That would have given me 256 square roots of 3 over 4. You check on that, but I'm believing 256 divided by 4 is going to give me that 64. Hey, let's get the area of that hexagon. Well, you say, well, we'll need an apothem. I say, yeah, we do. I'm going to show an equilateral triangle that exists in this hexagon. If you could show each of those radii to the vertices, those are radii of the polygon, then they would give us 6 equilateral triangles. How big are this? Oh, on this side of the triangle are 12, therefore all sides of that hexagon are 12. Let's show an apothem. Show any one of them, they're all going to be about the same size, but I'm thinking that this side would have been 6, as the full side would have been 12. That part would have been 6. The hypotenuse is 12 of that 30, 60, 90 triangle. Yeah, this is 60, it's true. That angle would have been 30. So the apothem of this triangle has got to be 6 times the square root of 3. So let's get the area of that hexagon. 1/2 times the perimeter of the hexagon. It's got 6 sides, and they're each of length 12. That has to be 72. Times the apothem, which is 6 times the square root of 3. And a half of 72 is going to give me 36. And 36 times 6 is 216. So we got 216 square roots of 3 for the area of the hexagon. And then they give us the total area. Well, I got to add up those parts. And okay, what could you do about that? I would begin with this whole number 96. You could put them in any order, I guess, but it'd be nicer. And then probably go with the number of pi units that we have, plus 50 pi. And then we can have the 216 and the 64 together, and that'll give us 280 pi, huh? No, excuse me, 280 square roots of 3. Another order would have been okay, but I'm liking that order. And you cannot add them any better than that. You can't put these pi's with those root 3's and this whole number. No, you can't do that. But that's a good looking answer for the sum of the areas of this composite figure. It's an interesting figure, isn't it? Let's figure out that area. I got an equilateral triangle with sides of length 6, and we want to find that shaded zone. If the sides are of length 6, now I'm thinking about the radii of these arcs of a circle, huh? And if the sides are of length 6, then that radius would have been 3, as that full length here would have been 6. So what would be the area of that whole circle is what I'm wondering about first. And it has to be pi times 3 squared, huh? That'd be 9 pi. But I'm wondering, since this is if that's an equilateral triangle, would that be a 60-degree angle right there? So what part of this circle is this place? I do want to get that shaded stuff, but I think I'm going to have to figure out what this other area adds up to. Because that 60 out of that 360, that's going to be 60, 360 is, hey, that's going to be 1/6, isn't it? 1/6 of the full area of that circle, which is 9 pi. And we got 1/6 of 9 pi, that would be 9 pi sixth, which can be reduced halfway to be 3 pi halves. I think that's the area of this part. I also think that's the area of this part. Each of those unshaded zones that I'm shading right now. So when I have 3 of those, that total area would be 3 times this much. That would be 9 pi halves. So I say to you, these white areas, other than this area that we seek, sum to 9 pi halves. And I think I would have to take the area of the triangle minus the area of these arcs of these sectors of circles to get the full area of this shaded zone. And what's the area of that equilateral triangle? Lots of ways you can do that, but I'm going to go with side squared, square root of 3 over 4. That'd be 36 square root of 3 over 4. And that'd be 9 square root of 3. Now that triangle's a lot bigger than those, not a lot bigger, but it's bigger than those 3 sectors. So I would say that the area's got to be the area of the triangle, 9 square roots of 3, minus the area of the 3 sectors. And that was 9 pi halves, wouldn't it? Man, that's not a very big number. I think it would be pretty fun to put that on a calculator, but it's a tiny little space, isn't it? Okay, let's go a little bit further. Check on that and get a look at that, though. A square is inscribed in this circle and it has diameter 18. I'm going to think about this being 9 and that being 9 because I'm going to want the radius of that circle, I'm sure. But this square, that's going to be a right angle here, isn't it? And if in fact it's a square, then these sides are congruent. We got a special triangle, don't we? That's an isosceles right triangle. This must be a 45, 45, 90. I'm going to need the sides of that square, aren't I? The hypotenuse is 18. I got to go from the hypotenuse to the congruent sides. I got to take the length of that hypotenuse and divide it by the square root of 2, which would yield 9 square roots of 2. That's how big the sides of that square are, huh? I expect what this question is about. It's not altogether clear. It's not written well. Is we're going to find the area of this shaded zone. I'm sure that's what I was expecting of us on this practice review. So let's find the area that I just did shade, which would have been the area of the circle minus the area of the square, huh? Is the area that I just did shade. Forgive me. So, hey man, what's the area of that circle? That would be 81 pi. Pi times that radius squared, 81 pi. Minus, well, what's the area of that square? And well, it's 9 root 2 times 9 root 2. And if you were to multiply those, 9 root 2 times 9 root 2, that's going to give you 81 square roots of 4. Square root of 2 times the square root of 2 gives you a full on 2. The square root of 4 is just 2. So this is 81 times 2. That's 162.